Так я вроде запустил трансляцию.
Так, то есть мне начинать, да? Shall I start?
Well, I think so. I don't see. Yeah, I think we can start. Igor is here. Игорь, ты здесь?
He's probably muted. He was here a second ago.
Okay, so I think we can start slowly.
So, Leon, you may start now.
Уже даже без тебя решили, что можно начинать. И вроде уже все записывается.
Okay, thank you very much for inviting me to the talk here. Let me first explain some motivation for this topic. In fact, I forgot to mention this is a joint project with Inna Mashanova, Vasya Krylov, and Alexei Lin. And in fact, we have two different motivations. The first is studying the monodromy of solutions of Bethe-Ansatz equations for XXX Heisenberg chain. So, namely, for me, this is the following. So the space of states for the XXX chain is a tensor product of evaluation representations of the Yangian assigned to any semi-simple Lie algebra G. Right, and the conservation laws for this magnetic chain generate some maximal commutative subalgebra in the operators in this space. Acted on by some. And in fact, this subalgebra, I will explain this, it comes from some universal commutative subalgebra in the Yangian. And it depends on a parameter from the maximal torus in the corresponding Lie group. So in fact, starting with Heisenberg XXX magnetic chain, I have a family of eigenbases in this space, depending on a parameter in the maximal torus of the group G. It turns that the dependence of the eigenbases on this parameter, there is some Bethe-Ansatz involved there. The dependence of the eigenbase on the parameter is given by some multivariate functions.
Leonid, sorry, question. I missed the definition. Lambdas are dominant weights or arbitrary weights?
Lambdas are integral dominant weights, so this is finite dimensional space.
Okay.
yeah, so I assume that everything is finite dimensional, and also I I could consider a bit more general commutative subalgebra depending on just on an element from the group G, but I restrict myself to the maximal torus. Because I'm interested in the joint eigenvalues, and almost every element from the group can be conjugated to the maximal torus. So in fact, it is sufficient. So the joint eigenvalues of the elements of this algebra, or the joint eigenvectors, are given by some multivariate functions in the parameter C. So it is natural to ask about monodromy of these eigenvectors. So hence we have monodromy problem. So and the goal is that we have some partial answer to this question about monodromy. We have partial solution. Namely, we can describe the monodromy along some paths in purely combinatorial terms. So at least we can there's some distinguished class of paths in the parameter space such that the monodromy is, and I will explain this. So and the second motivation, which is you'll see it seems very different, but it turns that they have much to do with each other. So my second motivation was to understand what is Kirillov-Reshetikhin crystal. So let me recall something. Like generally, crystals, in the sense of Kashiwara, is a combinatorial model for finite dimensional representations of the Lie algebra G. Finite dimensional G modules, where we represent the basis vectors of a G representation by vertices, some points, and represent the action of the Chevalier generators of G just by arrows connecting these vertices. So for example, for G equals SL2, we have just an SL2 crystal is a disjoint union of oriented graphs like this. So here, the vertices of the graph represent the elements of weight bases, and the arrows represent how the operator f acts on the weight basis. So we have similar picture for any semi-simple G, and such picture arises when you consider the representations of Q of G, the corresponding quantum group. Take or consider this representation as a representation of over the polynomials in Q, and take their so-called crystal bases and take the limit when Q goes to 0. So in this limit, you will have such combinatorial picture. And there, in fact, you can define such combinatorial objects axiomatically as some combinatorial monoidal category with some nice structures on it, and so on and so on. So this is a very good object, and but from this axiomatic combinatorial definition, it is not obvious, and you cannot expect from this definition anything similar for the affinely algebra, for finite dimensional representations of the affinely algebra. So in fact, for doing this crystal business, you always need some highest vector, and for finite dimensional modules over the affinely algebra you don't have such highest vector. So in general, you cannot do this, but for some reason, at least for some G-hat modules, there are crystals, and they are well defined and satisfy, and in fact they enjoy the most of good properties that Kashivara crystals do. For some modules over G-hat, we do have crystals. They are called Kirillov-Reshetikhin crystals. So the second goal is to explain how to construct such crystals. At least, at the moment, our construction works in type A, but we hope it generalizes to it.
What are these modules? Do they like contain finite dimensional or are contained in finite dimensionals?
Yeah, I mean finite dimensional models.
Okay, so not all finite dimensional, but some of them, right?
But not all finite dimensional models. In fact, I mean, you can, for example, you can take an evaluation model. You can take an irreducible G module and take the corresponding evaluation G hat module, evaluated at some point. Then, and for example, for G equals SL3, then it is easy to see that if lambda is proportional to fundamental weight, you can construct a crystal of such a presentation. But if your lambda is the highest weight of the adjoint representation, you already cannot.
Thank you.
Leonia, another question. In the A-type case, there is something like, I think it's called now the spectral duality, but it used to be called something else. But there is some kind of duality between the XXX spin chain and the KZ equation. On so if your G is SLN, then it should be like n point, maybe n plus 3 point KZ equation.
Right. So in fact,
on this twist parameter, right? So this monodromy you're talking about is it becomes the case monodromy of the KZ equation essentially, right?
Right. So
and the crystal limit is some kind of a quasi-classical limit in some direction, in the specific direction in the on the complex plane in the Planck constant.
Right. Let me explain. Thank you for this question. It is yeah. So this is really interesting. So yeah, Roma G hat is the current algebra, central extension of the current algebra, where the central parameter is, if we consider finite dimensional representation, then the central parameter should be 0. So it is just current algebra. Right. So in type A, we have GL and GL and duality, which interchange the XXX Heisenberg chain and trigonometric Gaden magnet chain. Yeah, and the trigonometric Gaden is the limit case of KZ. So in general, KZ is the connection, can be regarded as kappa connection and the Godin model arises when kappa goes to 0. So we don't have a connection in the limit, don't have a flat connection in the limit, rather we have just commuting operators in the tensor product of G modules. So then right. So then for tensor product of the representations involved in this JLM duality, we are really interested in some degenerate version of the case of the monodromy of KZ. So in fact, we are interested in so it is known that the monodromy of KZ is given by the braiding
But I thought that the Q parameter was something like exponential of 2 pi I kappa in 1 over
right.
kappa. Okay, 2
right.
pi I over kappa. Right. I see. Okay, good.
So yeah, so it is braiding for UQ of G modules, where Q is this. So we have to decide what we want to happen when kappa goes to 0, and what I want here, I want Q to also to go to 0. So for this, let me take kappa on the imaginary line. This way. Then I will have Q goes to 0. Then I will. So what I want here, I want to describe the monodromy of the eigenvectors for the Godin model as some degenerate version of the braiding when Q goes to 0. And in fact, this is possible. So the answer we have here is the following. So you can renormalize the R matrix. So the problem with taking this Q to 0 limit is that in the R matrix you have both Q and Q inverse. So the R matrix itself doesn't have any reasonable limit when Q goes to 0. But you can observe the following, that the composition, the R composition with R opposite is the operator. So for any pair of representations, is Q to the something like diagonal Casimir, one half of the diagonal Casimir acting in the standard product, and any maybe not one half actually, just Casimir. Then the idea is to normalize, to divide the R matrix by the square root of this. So you can consider Drinfield's unitarized So you just just make the braiding in symmetric just by force. But of course you you lose the braid relation, but on the other hand you get some operator which has a good limit when q goes to 0, and this is compatible with crystal bases, so it gives some combinatorial, well, it gives actually some bijection on crystals, and this is it is actually important for for this crystal business. And so our point is that we can describe the monodromy of the eigenvectors for Gaden model in terms of these Drinfield's unitarized geometries. But on the other hand, here the modules of the Yangian involved here are of the form symmetric or exterior powers of the vector representations Cn. But in fact, we expect that some good combinatorial description is also valid for some larger class of Yangian modules, not only symmetric or exterior powers. Okay. So now now let me say more precisely what is Bethe subalgebras. So let y of g be the Yangian of G, and G is any semi-simple Lie algebra. This is a Hopf algebra, which is well, in some sense unique Hopf algebra deformation of the universal enveloping of the current algebra. And roughly, this algebra is defined as follows. The current Lie algebra has evaluation representation lambda of Q for any complex number U, and from the Hopf algebra deformation, we wanted to have roughly the same representations, but the tensor product of such representation, we don't want to be symmetric. Rather, we want some rational solution of the Young-Baxter to give a natural homomorphism from tensor product in one order to the tensor product in inverse order. So, in fact, this rational solution of the Young-Baxter equation can be written universally. Yeah, Sasha, you are right. So this precisely this description we have only in type A, and in in other type, actually not in general, the evaluation representations cannot be deformed, but you always can add some lower terms to get something which does deform. Okay.
Leonie, I'm sorry, are these additional terms defined uniquely?
Mm.
So I mean, is there some general construction for this
Well,
total sum?
well, if you want to get an irreducible representation, then yes, they define. Because well, in fact, the finite dimensional irreducible representation is uniquely determined by its highest weight, and the highest weight is here. Okay. Okay, so now so this means that for any two representations, you have an R matrix. And in fact, you can get all these R matrices from something universal, living in some completion of the tensor square of the Yangian. So new. So is done. Okay. Then in fact this gives some natural so this is good system, some natural system of generators. In fact, this is a huge set of generators, but still it is very good for applications. So so you can take any to any finite dimensional representation of the Yangian, you can assign so let me denote it by V. You can assign the T operator TB of U, which is just the image Misha is asking, do we need the Yangian double for the universal arithmetics? Well, I think no. Maybe it depends on what you want from this universal matrix. So if you want the universal matrix depending on the parameter, then maybe. Well, at least for this, you don't need the double. So then you can define such an element from matrix algebra tensor Yangian. It's one. Then the Yang-Baxter equation implies the RTT equation on this element. So then you can regard the Fourier components of the matrix elements as the generators of the Yang. There is a nice result due to Curtis Wendland that you can take any non-trivial finite dimensional representation you get a system of you get a set of generators. And the RTT relation written here is almost the defining relation. Namely, for example, in the case of SLN, if you take the vector representation as V, then you by taking the matrix elements of the corresponding T matrix and the RTT relations as the defining relations, you'll get the Yangian of GLN. So to make it Yangian of SLN, you have to mod out the center. So the theorem of Wendland states that this holds in general. So you can define some algebra generated by Fourier components of matrix elements of the T operator with these relations, and if you additionally mod out the center, there is some recipe to do this, you get your Yangian of G. Okay. So now, this way of defining the Yangian by generators and relations is good for defining some commutative subalgebras. So, namely, let C be any group element then to any such element I can assign a subalgebra B of C Yangian, which is generated by traces of the T operator multiplied by C.
Could you please write the big brackets?
Sorry?
I mean, like other brackets like pi t in the brackets, right?
Where? So what should be in the brackets?
Like trace is applied to the product pi t, right?
To the right to the front. Generated by all Fourier components, of course, of this thing.
Leonid, I'm sorry, could you please recall once again, pi v is an operator acting where?
By v is a representation. So I denote by this the representation of the Yangian, so the homomorphism from the Yangian to the homomorphism of P, and I can extend. So it restricts to the Lie algebra G, and I can extend it also to the group. And I'm slightly abusing notation. So I am denoting by the same symbol, the representation of the corresponding leads.
Okay, and TV is an operator from the previous slide, right?
Right.
Okay.
So let me give an example. So if G is SLN or GLN, this is the same, almost. Then for the vector representation, the T operator is just the T operator. It has the standard Yangian generators Tij of U as matrix elements. And for other fundamental representations lambda k p. So let me denote it just by T of U. Then this operator is the following. It is antisymmetrizer multiplied by T of T1 of U, T2 of U minus 1, and so on. So this is an element in the kth tensor power of the matrix algebra tensor, the Yangian, and this is the projector to the kth exterior power. So then the definition is that gives you an algebra generated by trace T of U, trace lambda 2C T, well, A2 C1 U one, and so on. And this is the standard definition of the Bethe algebra in the Yangian of JLN.
I'm sorry, are we considering C equals 1 case?
Yeah, so in fact, this definition works for any C in the group. So and the problem I want to discuss here is that we get a family of maximal commutative subalgebras in the Yangian depending on a group element, and this family is not flat in general. So it is always non-flat. Namely, the size of the size of Bethe subalgebra of the identity is less than that of generic. Let's see. There's some comment. Yeah, so the nth antisymmetric product gives the quantum determinant, which in the Yangian of SLM is 0. Well, it's trivial. Sure. So you take k from 1 to n-1. So, and the problem with the size is the following. So if you consider Bethe subalgebra of the unity, then the first Fourier coefficient of trace T of U is central in the Yangian of GLN and should be mod out. So the Bethe subalgebra is smaller than for generics. So the coefficient of Q to -1 is central. But still, so what we can do, we can either stay on this and consider the non-flat family of commutative subalgebras, and their images in representations won't be always maximal commutative subalgebras, or we can do something different. We can consider all possible limits.
Leonid, I'm sorry, may I ask a clarifying question? By dimension here, you mean some graded dimension, right? Or
yeah, I mean the Poincare series with respect to some natural filtration on the Yangian.
And by flatness, you just mean a family with the constant Poincare series, right?
Right. Okay.
Yeah, thank you.
Right. So yeah. So in general, we can consider all possible limits Bethe subalgebras, and it will be some family of maximal commutative subalgebras of constant size.
Leonid, I'm sorry, limits to where? Oh, I mean, what do you
When so, for example, you can consider, instead of considering b of the unity, you can consider the limit of b of c when c goes to the unity.
But do you consider only limits c goes to identity or all others as well?
All others as well.
Okay, good. Thank
So,
you. Mhm.
so for example, if you consider all possible limits like this, so it actually depends on the path you are approaching the unity. So naively, you expect some blow up of the neighborhood of the unity. As a true space of parameters for this extended family of Bethe algebras. But in fact, the situation is more complicated. So what you get here as a parameter space is some compactification of set of regular elements of the group, in fact of the adjoint group, because the Bethe algebra doesn't depend, doesn't change when we multiply into a group element by something central. And in fact, we conjecture, this is our conjecture with Alex Ilin, that this compactification is some resolution of the de continue Purchase closure of G. I'm sorry, 1 second. I'm sorry. So there is some natural smooth closure of G, and we showed that the non-flat family of Bethe subalgebras extend to this closure, and when we consider the family of all possible limits of Bethe algebras, we get some iterated blow up of this space. This is the conjecture. No, the continued Purchase closure is not singular, but we still have to blow up something to get the true parameter space for the flat family of maximal commutative subalgebras.
Leonid, and for regular elements, the sizes are the same.
For regular element, the size is constant.
And if you take a non-regular element, then the size is larger. Is that true?
If you take non-regular, then the size of beta algebra is smaller.
Smaller, but I mean, you can't have a non-regular element with the same size of the beta algebra.
No, non-regular with the same size. Yeah, it is always smaller.
Okay, thank you.
Right, but actually, yeah, it is always smaller. Yeah, so let me give an example. What you can get by considering such limits. So if your group is SL2, then beta algebra, and let us restrict ourselves to the diagonal C. So C is C1, C2. Then beta subalgebra is generated by Fourier components of the linear combination. Sorry, there is a question. Yeah, on the blow up, the size is constant by the construction, right? Yeah, so beta subalgebra is generated by this. But here C1 and C2 are non-zero. And to compactify this space of parameter, you allow the matrix C to be degenerate. Yeah, in fact we can compare this with the Godin algebra story, and yeah, and in fact this is our main tool, actually, because we do know much about the eigenvectors for the Godin model and about their monodromy, and can use it here. Yeah, so if we allow the matrix C to be degenerate, then we get some limit beta subalgebra generated by Fourier components of just T11, and this is a Gelfand-Zetlin algebra. And another Gelfand-Zetlin subalgebra corresponding to T22.
I'm sorry, I'm a bit lost. What does the condition C1, C2 non-zero mean? So I mean, C is an element from the group, is it?
Right.
Then it's necessarily non-zero. So I mean,
then necessarily non-zero. But if we are constructing some compactification of the parameter space which classifies all possible limits of Bethe subalgebras.
Yeah, but I thought that the special point is identity. No?
Yeah, and also there is a special point at an identity where we have T11 of u plus T22 of u. So the first Fourier coefficient of this guy is dependent with the center. So so in the limit, if we consider the limit of such Bethe subalgebras when C goes to unity, we have an additional element T11 first minus T22 first, which is always present in the Bethe subalgebra for generic C. But it disappears in the naive definition of Bethe subalgebra. The subalgebra is unity, but if we take the limit, it survives.
Okay, thank you.
So and if we don't restrict to the torus, then we will have just something parameterized by 2x2 matrices up to multiplicative constant. So we have P3 as the parameter space, but we have to blow up this P3 at the unity, and this is the complete description of this parameter space of all possible limits at subalgebras in this 2x2. But in the general case, it is much more complicated, and I don't know the precise description. We don't restrict to the torus. Okay. Then the next theorem is that the closure of the regular points in the torus, parameterizing limits of P of C for diagonal C is the following. So let me formulate this theorem in type A. Let G so N. So then this closure is the following. One can regard the regular part of the torus as collections of pairwise different elements from C star. And in fact, Bethe algebra doesn't change if we multiply all these z's by the same number, so it is up to proportionality. So, and this can be regarded as a point on the modular space of stable rational curves with n plus 2 mark points. And in fact, the right parameter space for Bethe subalgebras corresponding to diagonal matrices here is the Deligne-Mumford closure. So and in general, in the general case, there is also some analog of this space. Namely, you have to take the analog of the lossif-Manin space, namely the toric variety corresponding to the fan formed by well chambers, and take the continued Procesi wonderful closure of the complement to the root subtori. So let me say that this generalizes any G, and the construction generalizing this is due to the continuum. So
Leonid, I'm sorry, could you please repeat once again what's the role of the lossif-Manin toric variety?
yeah, so you can regard the in fact you can construct the Deligne-Mumford closure, this one, in 2 steps. So you can first you can first allow first why n plus 2, because we have n mark points z1 zn, and also we have 0 and infinity, right? Then you can construct the Deligne-Mumford closure in 2 steps. So first you can allow the nodal curves of this caterpillar form such that the 0 point is on the first component, and the infinity is on the last. And the eyes are splitted between other components, and you allow the I and the J to coincide, and after that you blow up all indecomposable diagonals. So first you allow this, and second you blow up yeah. So in lossif-Manin space appears. So, and this is a type A story. So, and for general G, we replaced the loss of money in space by some toric variety. So note that loss of money in space is a toric variety. So it is a complete toric variety corresponding. It is defined only for AN root system, and this is a complete toric variety. But you can define similar toric variety for any root system just by taking by constructing toric variety from the fan formed by Weyl chambers. This is straightforward definition of straightforward generalization of the loss of money space. And after that, you blow up all indecomposable intersections of root subtori on this toric variety.
Sorry, could you please give the reference for this Weyl chamber construction? I mean, more general one construction.
There is a paper of the continuity where
Okay, thanks.
they describe the actually what they describe there is a multiplicative version of the Contini-Procesi wonderful closure for hyperplane arrangement.
I'm sorry. So like, if we go back to type A, this blow up of loss of money is equivalent to G Contini-Procesi, right?
Yeah. So yeah. So this blow up is just the blow up of all indecomposable intersections. Of the boundary divisor. So we need to blow up all of them to get the Contini-Procesi.
So, but the loss of money is already compact and smooth. You don't need to blow up anything. So it's actually
right, but loss of money in space is good, but it parameterizes something different. It is not sufficient for parameterizing all limits of Bethe subalgebra. Because you actually can assign a Bethe subalgebra to any point of loss of money in space, but the size of Bethe subalgebras corresponding to boundary point will be smaller. So you have to blow up these boundary points to get more parameters to describe all possible limits. Okay, so now the next following. So we can consider all such Bethe subalgebras in the Yangian of SLN. Where C now is in the Lin-Mumford boundary space. Then there is an open dense subset n such that B of C acts on B on the one of one, so on, and then B on the n of n. The cyclic vector. All also.
Leonia, I'm sorry, what is the capital N?
And well, n is some natural some positive integer.
No, I don't understand the statement. So how does the claim depends on this subset?
Okay, so let me wait. Let me
Oh,
reformulate.
you mean the parameters belong to this C to the N, or?
So let us fix n.
N is just a number of factors, right?
Just a number of factors.
Okay.
And,
Thank you.
and fix highest weights, lambda 1, lambda n. Then for generic evaluation parameters, all Bethe subalgebras act with cyclic vector on such tensor. And in fact, we have a bit more. These tensor factors can be not only evaluation representations, but any skew representations assigned to a skew Young diagram. And the same will be also true.
Leonin, do you have examples when this property does not hold? So I mean, some use where the cyclic vector does not exist.
Yeah, there are examples.
Oh, okay.
So something bad happens when this tensor product is reducible, and when you have some isomorphic simple factors in the Jordan Holder series. So there are actually examples. So unfortunately, this is not always. But this is true for generic parameters, and for generic evaluation parameters. So then we have corollary. So once the Bethe algebra acts semi-simply, and it has a simple spectrum. Under the conditions of that theorem. And Bethe algebra acts semi-simply. So for this, it is sufficient to have some Hermitian form. such that Bethe subalgebra acts by normal operators. And this is satisfied in actually two opposite cases. At least we know two we know two cases where we can guarantee this property. So the first case is when the evaluation parameters are real and C is real as well. So C belongs to M0 n plus 2 to the real form of the Degenerate space, which is the closure of the regular elements in the split torus. Split real torus. And another case corresponds to C in the closure of the regular part of the compact torus. So this is a Deligne-Mumford closure of the configuration space of the points on a circle. And in this case, we have some restrictions on both evaluation parameters and the highest weights. So the highest weights lambda I should be rectangular Young diagrams, and the UI should be on shifted vertical lines, plus some constant depending on lambda.
Sorry, I'm lost. You say Deligny-Mumford, so you somehow use both compactifications?
Both. What is the second one?
Loss of money one.
No, I use only Deligny-Mumford, but I have explained that the Deligny-Mumford is some iterated blow up of loss of money. So I
Okay. Well, okay.
I don't mean actually loss of money here.
Sorry. So whenever you write M0 n plus 2, that means anyway Deligny-Mumford compactification, right?
Right.
Okay. Thanks.
Mm-hmm. Yeah. So the second case is for me it is much more interesting, and it was actually this goes back to Kirillov and Reshetikhin. So, but in both cases, we can regard the eigenbasis for. So corollary can regard joint basis the representation as covering of either n plus 2 bar of R in the real case, or this another real form of the Deligne-Mumford space. Let me denote it this way, or maybe maybe let me denote it this way. In the compact case, so we get an action of the fundamental group of such space on the eigenbasis. And so we conjecture that this action always has combinatorial description. So and actually the combinatorics is different in these two cases. So in the first case, it is related to Bernstein-Kirillov group. So they constructed some group generated by involutions acting on the Gelfand-Setlin polytope. This is because the subalgebra, the Bethe subalgebra corresponding to the most degenerate curve like this, the caterpillar curve, so the subalgebra corresponding to this curve is Gelfand-Setlin subalgebra, and its eigenbasis is the Gelfand-Setlin basis, and this basis is in one-to-one correspondence with integer points in the Gelfand-Setlin polytope, and we expect that the fundamental group, the corresponding fundamental group, acts by so-called Bender-Knuth involutions of this Gelfand-Setlin polytope, and in this second case, we expect the following. We expect that there is a not expect, actually, this is a theorem Vasa Krylov. In Shanova and myself. But there is a natural structure of Kirillov-Reshetikhin crystal on the spectrum of Bethe subalgebra in the corresponding representation. And the monodromy action of the fundamental group is given by some partial Schutzenberger involutions of this Kirillov-Reshetikhin crystal. So maybe I have no time to explain what it is, but it is some purely combinatorial construction in terms of just in terms of special practice. So these results actually generalize our joint results with Joel Kamnitzer Eva Halasheva and Alex X. Where we actually do the same for Godin model. Okay, so yeah, so maybe maybe it is a good point to stop and I can ask questions if there are questions. Thank you very much.
Okay. Other questions?
Yeah, Leonia, could you please go to the previous slide? Yeah, thank you. So there was a theorem and then a corollary. In which sense it is corollary? I mean, the first error, like if it's semi-simple, then it has.
Then it has simple spectrum because simplicity together with the vector property implies simple spectrum, right?
Yes, but is it an implication on a dense subset, like in the theorem?
Yeah, so I had to write here assume this U1 to N belongs to this dense subset. Well, this open subset.
But what's about the other arrows? Like if like this 1 and 2 cases, if we assume this 1 or 2 case, are we automatically in this dense subset, or we need some additional constraints?
Yeah, this is a good question. So it is not automatically. Moreover, in the first case, there are some specific values of the evaluation parameters where the subalgebra doesn't have specific vector. So the only thing I can say is that this open subset intersection of it with this half-dimensional real subvariety with this real form is still open then. And the same for the second case, but in the second case, I believe that in fact the cyclic vector property is always satisfied.
Thank you.
Okay. If there are no questions, then just thanks, speaker. And спасибо, Лёнь. And we meet next Monday. There would be a talk of Sergei Barannikov. He will send me as soon as possible his title and abstract so we can put it on the website. Thank you.
Thank you very much.